Record. Yeah. Okay. So I recall the idea. That we want to come to Fourier series, not straightforwardly, and people do typically in the book of trigonometric series and so on, but through abstract framework, through Euclidean and Hilbert spaces. And in this way, we shall study Fourier. And in parallel, we shall have machinery to consider other systems which are not Fourier, but which are used also in many applications. So my aim is not stop on Fourier analysis. I start with to repeat what we introduced. Everything is in this text which I send you, so you can even read it. If you don't want to follow a lecture, you can read everything. So first was notion of metric space. Oops, if it is visible. Metric space. So it is some set X of any origin where there is metric row. The distance, analog of the distance. Metric has all properties where we get the notion of metric. The simplest metric is on the real line, and it is just X minus Y on the real line. Now, you spent many years by studying analysis on the real line. You studied a lot. Limits, convergence, and so on. Now, if you go to your course, which you studied, and everywhere change absolute value to the distance, you will get similar theory on metric spaces. First of all, we need the notion of convergent sequence. So sequence xn, but now these are vectors belonging, it's not even vectors, metric space need not be vector space. It can be any set, And we want to give definition, what does it mean? Xn converge to X and go to infinity. It's the same as was in real analysis. For any epsilon larger than 0, there exists such number depending on epsilon. For any n larger or equal this number, instead of absolute value, we write distance between xn and x is less than epsilon. So the definition of that xn converge to x is the same as was in your usual course of mathematical analysis. This can be formulated in other words. It's equivalent. The definition is equivalent. That limit and go to infinity, distance xn x is equal to 0. So this epsilon definition is just a definition that the distance between xn and x goes to 0. Okay, so this is definition. Then we consider examples of sequences which converge not on real line, but in metric spaces. So I will not, for the moment, go in more details because my aim is to approach Fourier series. Now, we go back to real line. And on real line, if you have a good course of analysis, I think in any course of analysis, you have the notion Cauchy sequence. So this is such sequence, first on the real line, xn, which xn minus xm goes to 0 and m goes to infinity. So this is Cauchy. In some books they call this fundamental sequence, but in majority books it's called Cauchy sequence in the name of Cauchy, German mathematician. As you know, Germans, they are such crazy guys, they want everything should be very rigorous, very ordered, and so on. Before Cauchy, nobody used epsilon. People just tell xn is near x, and therefore it's approximately x, so this means that x is limit of xn. But Cauchy introduced this definition and started to write letters to mathematicians. And more in this discussions that xn is very near to x, he started to find mistakes and destroy the reasoning without epsilon. Of course, epsilon is formalization. On the other hand, I don't know what was your experience of limit in this school or where you get it at university. Very long time I was really disappointed by this epsilon and so on. So I don't know, maybe it was my personal. I had very big problem to understand what is the limit, but okay. So this is Cauchy sequence. How we generalize the notion of Cauchy sequence to metric space? So now X row, Cauchy in metric space, so Xn, then distance Xn minus Xm goes to 0 and m go to infinity. So this is Cauchy sequence in metric space. As I told, everything is done automatically. Everywhere it change absolute value to the distance. Now, why Cauchy sequence is very important in your analysis, in your course of analysis? I hope that your teacher discuss this point. First of all, first of all, we are on real line. If lim n to infinity xn equal x, this implies xn is a Cauchy sequence. So any convergent sequence is Cauchy sequence. It is very easy to check, and we shall check this directly in metric space. So if sequence is convergent, then it is Cauchy sequence. Now, what is more important and what is not so easy to prove? I don't know how your teacher did this. Vice versa is correct. If xn is a Cauchy sequence, this implies they exist limit and go to infinity xn x some real number. So any Cauchy sequence of real numbers has the limit, and this within real numbers. So I don't know, what is your recollection? Did your teacher discuss this, that notion of convergence is equivalent to the notion of Cauchy sequence within real numbers? Yeah.
In our courses in our courses in analysis, we haven't studied Cauchy sequences.
But how you did this? Because what was your definition of real number? How your teacher defined to you real number? It's neither so simple. Just maybe as fraction, yeah, as decimal fraction, not.
Yeah, I think we define real numbers as
infinite decimal fraction, yeah?
Yes.
Yeah. So, for example, this, yeah. In this way, you can prove this. Okay, so this is, but maybe even when your teacher told you that the difficulty is big, that if sequence is Cauchy, then a limit exists. You should find this limit, some point in real number. Maybe when your teacher told you about this, he maybe remarked that maybe not. Instead of real numbers, we consider Q rational numbers. Rational numbers. Then B is not correct. In rational numbers, it can be Cauchy sequence without rational limit. Exist xn, many such xn's, Cauchy sequences, but without limit without lim belonging to Q. And it's clear why, because limit would be in real numbers. Because this field of the set of rational numbers is subset of real, and typically if it has no limit in rational, it has limit in real. No, the simplest example is we know it should be some sequence which converge to irrational number. And we know that it converges to E, the basis of exponent, and this E does not belong to rational numbers. In principle, I don't remember how people prove that E is not rational. I don't remember. You should remember, not?
I haven't really studied why it is irrational.
I don't remember. So maybe even our teacher never proved this. He just told that E is not rational number. Okay. So now we see that we have two different metric spaces. Real numbers with the distance given by absolute value, and rational number with the distance given by the same metric. So distance is the same, but sets are different. We see that these metric spaces, these are metric spaces, both sets with this distance are metric spaces. These metric spaces are very different with respect to characterization of convergence with Cauchy sequences. Here, any Cauchy sequence has limit. Here, there can exist Cauchy sequences without limit. So Q and real numbers are very different from the viewpoint of characterization of convergence with Cauchy sequences. Now we would like to formalize this difference in the abstract framework. And we consider two classes of metric spaces. We give the definition. So we again have seen the difference on simple example. And now we make abstract definition. X row is called complete if any Cauchy sequence a limit in X. So real numbers is complete metric space. So the set of real numbers is complete metric space. In the opposite case, space is called incomplete. In the opposite case, X row is incomplete. So rational numbers, the set of rational numbers is incomplete metric space. Why complete is good? Because we shall see this when we come to series. We would like to study series in metric spaces. Then it is very easy to study them at Cauchy sequences. So, and then to say that a series converge is enough to prove that its partial sum is Cauchy sequence. So this machinery would work for our Fourier series, which will come later. Okay, now we need not so general case metric spaces. We need something much more restricted, and we introduce the notion of normed space. Normed space. So let us. So normed space. Here, additional property, linearity. It is a linear space. So they are vectors, or vector space. Is a vector, and the other books it's linear space. Plus this defined norm. This defined norm, some function which satisfy some axioms. Normed space in particular is metric space. So if X norm is normed space, here we can introduce metric, the distance, which is norm X minus Y. So in particular, it is metric space. So for any normed space, we can use the general ideology of metric spaces. So in particular, we can consider complete normed spaces and incomplete metric spaces. So complete normed space is called Banach space. It has special name. Banach space. In the name of Stefan Banach, who was one of the founders of this abstract analysis on linear spaces. Banach space in the name of Stefan Banach. Okay, so in Banach space, any Cauchy sequence has a limit belonging to this space. If space is not Banach, there can exist a sequence without limit in this space. Now examples of Banach spaces. Of course, real line is one-dimensional linear space. Then we can consider X Cartesian product of real lines, so vectors with n coordinates. So X, X1, X, n is not good, we use this for convergence, Rm, Am. Yeah, such vectors. And sequence, if you want sequence, we put upper index for sequence. So now it would be, so each coordinate has upper index. So if you consider sequence of vectors, n is index for sequence, n equal 1 to up to infinity. And here we can introduce different norms on this Cartesian product of real spaces. Different norms, yeah? So, for example, we use norm 1. Then, what does it mean that X is limit n to infinity xn? X also vector. It means that, for example, if we use norm 1, x minus xn, norm 1, what it was the norm? Sum g from 1 to 2m, and here is xg minus xgn, and this should go to 0 and go to infinity. So it means that x is limit xn with respect to this norm. We also would be even more interested in Euclidean norm, which is more or less given by Pythagorean theorem. I write the square of it because I should take square root, and it's not maybe so nice to write square root. So it is this sum g from 1 to infinity xg minus xgn square. Or not infinity, infinity will come later, 2m. So we take two vectors, vector with coordinates xg, and vector with coordinates xgn, and this should go to zero. This should go to zero. There was some communication from. No communication. I saw some chat. No chat. Yeah, okay. So, yeah. What I want to tell that we shall not prove this. It's subject of another course, functional analysis. But it is easy to prove that as real line was complete, any of the spaces are also complete. So, you can write in this way as mini theorem, which we will not prove, but it is proven quite easily. It's not difficult. Theorem An with any of norms, and we introduce three. This, which is sum of absolute values, 2, which is sum of squares, and what also was infinity, which was maximum, is complete. It's a Banach space. It's Banach space. Banach space. So complete normed space. Any Cauchy sequence has a limit in this space. So any sequence of vectors, which is Cauchy sequence, is convergent to some vector belonging to Rn. Belonging to Rn. Okay, now we go what we want to go. We need also scalar product. We need also scalar product, and we go to Euclidean spaces. Yeah. So we report what is metric space, what is normed space, and now we go to Euclidean spaces. We need scalar product. We need scalar product. So X with scalar product is a Euclidean space. Euclidean space is Euclidean space. We proved last time that we can introduce the norm on this space, square, which is just xx. So we prove that it really satisfies triangle inequality by using Cauchy-Bunyakovsky-Schwarz inequality. So this is the square of this scalar product is norm. Okay, we're right. This is norm. So this is normed space. So any Euclidean space is automatically normed space. So it is enough to introduce scalar product, and then automatically you can define the norm of this space. Now, of course, as any normed spaces can be complete and not complete, Banach or not Banach. And we are interested, of course, it is good to work in complete space. Now look, you have a good course of analysis on real line, but there is no any course of analysis over rational numbers. There is a geometry over rational numbers, algebraic geometry, but not analysis. So therefore, if you want some analysis, incomplete Euclidean space is not good. So, and we consider very special class of Euclidean spaces and give such definition. A complete Euclidean space is called Hilbert space. Hilbert space. Hilbert space. In the name of David Hilbert, who was German mathematician, I already told you that it's very good to be a mathematician because you will be memorized for hundreds and maybe thousands years, yeah? So everybody will forget Trump, Putin, Hitler, everybody would be forgotten. But Hilbert would be known to everybody. Euclid is known for 2000 years, and he just formulated 3 or 4 axioms. 4 axioms are known for 200,000 years. Oh, not 200,000, just for 2,000. But maybe he will be known even in 200,000 years, because your grandchildren still will study Euclidean spaces and Hilbert spaces. Yeah, so this is Hilbert space. Space where we have scalar product, have the norm given by scalar product, and any Cauchy sequence has the limit inside this space. Any Cauchy sequence has the limit inside this space. So we consider the simplest example of Hilbert space, which we have already considered. Example of Hilbert space is maybe this right better. L2 space. So this is the space which have vectors with infinitely many coordinates, such that the sum g from 1 to infinity xg square is less than infinity. All squares are able sequences of real numbers. So, for example, sequence 1 over n is in this space. 1 over square of n is not in this space. Here also very interesting. Look, this and this will be the object of Fourier analysis. So there are infinitely many coordinates. Infinity is not your natural notion. Where you meet infinity, it seems that there is no infinity in this world. But Fourier series, these are infinite series. And real electromagnetic signals, they have infinitely many components. So this is very interesting. You have a signal from mobile. Signal is just a physical thing. But this physical thing can be described only with infinitely many coordinates. What is infinity? It's not so easy to understand. And this is also the point maybe to point on, as it was the statement of Wigner, famous physicist, that the success of mathematics in describing of physical world is unexplainable. So in some way we cannot explain why mathematics match this world so good. So there exist even theological philosophers who think that this universe was created by mathematical laws, and we discover mathematical laws, so we discovered this universe. But it's really surprising, because these equations, they describe so well this world that one can say why it is so. Okay, this space here was scalar product given by xy was the sum xg yg. The norm square was just the sum of squares. And it is possible to prove that it is complete. So this against theorem which we will not prove. L2 is a Hilbert space. A Hilbert space. Now, and consider another example. We shall have two basic examples. One. 2. Consider now, in fact, these are more or less the same space, but define it in different way. Consider L2 of some segment AB. So these are all functions, phi from AB to real line. We have considered, I think, already last lecture. Such integral from AB square phi x dx, or maybe phi t dt is less than infinity. Square integrable function. Functions which are square integrable. AB can be even a whole real line, so from minus infinity to infinity. So the space of square integrable functions on the segment AB. It is also Hilbert space. Again, mini theorem. L2 AB is a complete Euclidean space, is a Hilbert space. Hilbert space. Scalar product is given by integral of the product of two functions. Scalar product of two functions is just integral. Let us write phi psi is integral from AB phi t psi t dt. So this is space of functions, and here will appear our Fourier series. So our Fourier series, these are functional series, and they will appear as elements of this space. But the whole machinery we shall do in abstract way. In abstract way. Finally, we will come here in this space, but everything we would like to do in abstract Hilbert spaces. Okay, so now these were examples. We gave definition of Hilbert space. These are examples. Now we prove some properties of abstract Hilbert spaces. We are going very well, and I think on the second hour we shall approach our aim. Trigonometric series and Fourier series. So, but before we need some machinery. So typically Hilbert spaces are denoted by H in the name of Hilbert. Let H be scalar product be a Hilbert space. So this is complete Euclidean space. This is complete space with scalar product. Then already in the course of algebra, you know the notion of orthogonal vectors, of linear algebra, yeah? So U orthogonal V, if scalar product is D. So such vectors are called orthogonal. Now, in the course of linear algebra, you had the notion of basis. En is called a basis if any x in H can be represented as sum. Here some coefficients Cn, and here these basis elements. But now we shall consider sums from 1 to infinity, because, for example, I shall illustrate this by this L2 example. Example of basis. Suppose we are in L2 and consider vector En, which has 0, 0, 0. So the place n is 1 and all others are zeros. So this place is n. Then, of course, any x which is sequence x1, xn, and so on. We can write some g from 1 to infinity, xg, eg. So the sequence of x1, xn, and so on can be written in this way. We multiply this vector and they appear xg only in this place. And when we make the sum, we reproduce this vector. But coming back to definition, here is the infinite sum. So we need the notion of convergent series in normed space. In particular in Hilbert space. So what is the meaning that some series converge in the normed space? No, it's more or less as usual series converge, so there is no difference. So now we go a little bit back to normed spaces. Definition. Let, for example, X be a normed space, then some sum from G from 1 to infinity, some vectors, for example, UG, where UG belongs to our X, it converges to U also vector in this X. If what was definition in usual course of analysis? You should consider partial sums, Sn, and you simply copy it from your analysis. Okay. UG, partial sum, as you do in usual analysis. But now UG are not numbers, but vectors. So we should now write the norm Sn minus S. And if it go to 0 and go to infinity, then we say that this series converge UG and its sum is log S. I will not give you infinite dimensional examples because we shall see them in the theory of Fourier series. So if the sequence of partial sums, and this is again vector, the sum of vectors is again vector. If there exists such vector in our space, S is also a vector, such Sn minus S norm goes to 0, then we say that this series converge. In normal space. In particular, in Hilbert space, norm is very special. And now we would like to explore specialty of norm. In Hilbert space, norm is very special. It's X. So now we would like to explore a specialty of the norm of Hilbert space and get some criteria for convergence of series. Okay, so now we go back to Hilbert space. And we get definition of orthonormal basis. Definition. Let H be a Hilbert space. Then Pn is called orthonormal basis, also normal basis is if First of all, En, Em is equal Kronecker symbol delta NM. So 1 N equal M and 0 N not equal M. And any X can be represented as the some coefficient, let us call it 6n, and xn is real number. X real number. Well, series converge in the sense that I told you with respect to the norm in this space. In this space. With respect to the norm in this space. Numbers in the expansion of our vector with respect to this concrete orthonormal basis, so xn is a Fourier coefficient, or we write with respect to this orthonormal basis. Normal basis. So in Hilbert space, in Hilbert space, we can fix orthonormal basis such that say products are such. And then we can expand any x with respect to this basis and call these coefficients Fourier coefficients with respect to this orthonormal basis. Usual Fourier coefficients would be for very special basis, which is given by trigonometric functions. So we will approach trigonometric series from very, very abstract level. Yeah. Okay, so we know what is orthonormal basis, we know what is Fourier coefficient. Now let us find how we can find Fourier coefficient through vector x. So we can do the following. This is more a standard technology. Let us multiply both sides of this equation by some concrete vector, for example, with index m. Multiply in the sense of scalar product. So here would be x, scalar product em, and here would be sum xn, en, em. Yeah, we have such equality. So we multiply with respect to scalar product, both sides. Now we know that scalar product is linear with respect to both arguments. So we can change sum with scalar product, and we can take away number. So we can write this. Maybe since it is very important equality, I will lift this up. I'll lift this up. It would be sum. Xn is also just real number, it go out from scalar product. And here En, Em. But this is delta symbol of Kronecker. It's survive only when N is equal M. So this is X is index M. So we derive at this formula for Fourier coefficients. It is equal X scalar product Em. So this is the formula for Fourier coefficients. It's enough to multiply our vector by basis vector with number m in the sense of scalar product. And it works for any orthonormal basis. It works for any orthonormal basis. For any orthonormal basis. Now we prove the following Oh, we have 2 minutes. I think we should prove. We prove the following theorem. Here we prove because it is important for us. So let En be an orthonormal basis. Normal basis. Then for any x in H, we have the following equality. Norm x square is equal sum xg square of its Fourier coefficients. So it's more or less Pythagoras theorem in abstract framework of Hilbert spaces. So it's the square of, this is square of hypotenuse, and this is the sum of squares of cathets. So this is a kind of infinitely dimensional Pythagoras theorem. So to find the length of vector, we should take all its coordinates, square them, and get this sum. And this equality also has the name. It's very famous, and this is who are engineers, you will use it. It is used in wireless communication and electrical engineering everywhere. It's called Parseval equality. Parseval equality. As I told already, square of the norm of signal is energy, is total energy. And coefficients give us the modes of signals or its frequencies. For example, G can be frequency of signal. So how much of signal going to different frequencies. So this formula from physical viewpoint is very natural. So the total energy of signal is equal to the sum of energies with respect to all frequencies. For example, if G give us frequency, we can send radio signal on different, it has on different frequencies. Then the total energy of signal is the sum of energies of these blocks, which goes on different frequencies. It can be polarizations, G can have different physical meaning. So this formula is about splitting of typically signal or electrical flow into some blocks, and then just summation give us total energy. No, okay, now we make break 10 minutes, and then we prove this Parseval equality. We prove this Parseval equality. Now I want to make smaller file size. Stop. How to stop recording? Reactions. Share. Recording. We are here. Recording.